I'm John Fox. What I'm going to describe today is joint work with Brad Price, who's at West Virginia University, and has newly joined Sandy Weisberg and me in developing the car and effects packages. Both of these are venerable packages. I just checked, actually, and discovered that the car package was first contributed to CRAN in 2001, and the effects package in 2003. Okay, so they've been there quite a long time. The packages are associated with the book that is written by Sandy Weisberg and me, called an R companion to applied regression. That book is about to go into a third edition. It should be out approximately in October, and that provides us with an occasion to update and improve the package, which hasn't had a major overhaul since the previous edition of this book, which was in 2011. So we have new versions of both of these packages. The packages are in quite wide use, particularly the car package, and I think that that conveyed with it a responsibility to not break things in other packages. So where we could, we've made the changes upwards compatible. Even though, for example, in the effects package, we've fairly comprehensively reorganized the arguments to the functions in that package, as well as introducing new functions. We've also retained the old argument structure as legacy arguments, so that to the extent that we could, code that used to work with the package, with these packages, still does. Okay. Another thing that we've done is we've taken data out of the packages and put them into a data-only package called car data, which is required both by the car and effects package. Partly because the packages, particularly the car package, was getting rather unwieldy with too many objects in it. Okay, the versions that I'm about to describe, this says, are the versions that are currently on CRAN, but that's not quite right. Car 3.0.0 is on CRAN. I had anticipated that by the time of this talk, we would have updated that to car 3.01, which is essentially, which pretty much just fixes minor bugs in the 0.0 release. But we haven't been able to do that quite yet. The effects package 4.0-2 is indeed the version that's currently on CRAN. The focus of the car package is tools for applied regression analysis. The name of the package is an acronym from the book, that is, Companion to Applied Regression. And these tools are meant to apply broadly to regression analysis. So in particular, linear models, generalized linear models, mixed effects models, but some other regression models as well. And our intent is to address all of the phases of an applied regression analysis, from importing data, although there are, of course, other facilities in R for doing that, through preparing, examining, transforming data prior to a regression analysis, and then subsequent to analysis, model critique, that is what's often termed regression diagnostics, and tools for testing, summarizing, and comparing regression models. The effects package has a bit of a different focus. It focuses on interpretation, particularly graphical interpretation of complex regression models. For instance, models that have things like interactions in them, or polynomial terms, or spline terms, which require visualization generally in order to comprehend what the model is saying about the data. But in the most recent incarnation of the CAR package, we also include, of the effects package, we also include some diagnostics that are generalizations of partial residual plots, or also called component plus residual plots. So we're able to visualize the fit of the model in relation to the data for models with arbitrarily complex interactions, for example. I'm going to show you some of this in some quick examples, but first let me highlight some of the new features in each of these packages. We have a new function for bootstrapping in the CAR package, which essentially provides a convenient front end to the boot package, which works easily in simple situations. We also have several new functions for summarizing statistical models and certain other sorts of objects, which we think of as sort of plug-in replacements for some of the standard functions in R that provide, in most cases, additional functionality. So you can see several of them here. We've provided a method for the standard R influence generic that applies to mixed effects models and allows one to examine influence both of clusters of cases and of individual cases on a fitted mixed model or linear or generalized mixed model. We have a new function for testing proportional odds in models fit by the POLR function in the mass package. We have some new functionality along with improved functionality for maximum likelihood-like selection of transformations in regression. And this includes a new family of transformations related to the Box-Cox family, but that allow 0 and negative values in variables to be transformed. We've also tried to regularize and improve the arguments to the graphics functions in the CAR package, which we felt were somewhat confusing and non-standard in the previous iteration of the package. In the effects package, we have a new way of thinking about effects of predictors in a regression model, which focuses on a particular predictor rather than on terms in the model, which is what we had emphasized previously. The general idea is similar, but it's implemented in two new functions. One, predictor effect, which focuses on a particular predictor selected by the user, and two, predictor effects plural, which will draw all of the predictor effect plots. We feel that predictor effects, first of all, have invariance properties that aren't necessarily shared by what we would now term effects, say focusing on a particular interaction in a linear or generalized linear model, and as well have a simpler interpretation. We've also added, as I mentioned briefly earlier, partial residuals to effect plots for linear and generalized linear models. And this actually works for mixed effects models as well, as a way of checking whether the functional form of the model adequately captures the configuration of the data. And in the most recent version of the effects package, we've also implemented partial residuals for factors, that is, not just for numeric explanatory variables. We put quite a bit of effort into improving the way in which the arguments to the functions in the effect package works, in particular the plot methods, which had something like nearly 40 arguments in the previous incarnation, leading to many requests for help and a lot of confusion. We've now consolidated those into a much smaller number of list-like arguments. And there are also improvements that are invisible to a user, but which make it much easier to extend the effect package to other classes of models. Some of this will just work. That is, we have a more robust default method than we had before. But even when it doesn't, the default method doesn't work without additional attention, it becomes much easier to write a specific method for a new class of statistical models, which then calls the default method. And we support directly in the package a number of classes of statistical models in a variety of other packages, but we also encourage other people to develop effect methods for models in their packages. Okay, so I have a few illustrations, and let's start with the car package. And I'll show you two examples. One of them involves fitting a least squares regression to data on bank transactions, incidentally, as you'll see, at an Australian bank. So this is some inadvertent local content. And then I'll look at fitting a generalized linear mixed model to data on police stops in Minneapolis. Okay, so here's the bank transaction data. It's in the transact data frame in the car data package, which loads along with the car package. One of the functions in the car package is brief, which is intended to produce brief printouts of objects. It's intended to be a kind of substitute for print. So this is what brief does with a data frame, for example. And here we have data on 261 branches of an Australian bank. And in each branch, we have the number of transactions of two different types, called T1 and T2, and the amount of time in minutes spent by the staff in the branch. So we're interested in determining how much time is taken by each kind of transaction. So this is, in a sense, a straightforward problem. We just regress time on T1 and T2. The intercept is the average amount of non-transaction time spent in the branches. And the coefficients of T1 and T2 are the average number of minutes spent in each of these two kinds of transactions. And this is an example of our S function with the additional argument brief equals true, just to compress the output a little bit so it fit on the slide, which we think of as a kind of substitute for the summary function. Okay, but as it turns out, there is a problem here, and that is that the residuals are heteroscedastic. That is, as the predicted values, the fitted values increase, as one might expect with data like these, the variation of the residuals increases as well. And a score test of non-constant error variance provided by the NCV test function in the car package suggests that that's not a chance pattern. So what to do? There are a couple of obvious approaches. One of them is to try to correct the standard errors of the least squares estimates for non-constant variance. Another probably better approach, and used in the original source, for example, is to fit a gamma regression model where the non-constant conditional variance is built in. Okay, but at the moment, I'll show you the first approach. And in the car package, we make it easy to use alternative coefficient covariance matrix estimators. For example, sandwich estimators or an estimator based on the bootstrap. We can simply plug these in. So here, for example, are the standard errors that we would get with the brief function applied to the linear model, calculating the coefficient variance covariance matrix with the sandwich estimator provided by the HCCM function in the car package. But you could equally easily use a function in the sandwich package here as well. If I want to produce wall tests of the terms in the model, not terribly exciting here because each term has just 1 degree of freedom and the model is additive. Likewise, we can plug in HCCM to calculate the coefficient covariance matrix for the ANOVA function and get type 2 wall tests. Here, I instead use the bootstrap. So I've set the seed for R's random number generator to a known value and then bootstrapped the regression model and calculated a coefficient covariance matrix based on the bootstrap estimates. And again, that can simply be plugged into a function like brief or ANOVA, and indeed these work in a uniform way. Our confint function, given a bootstrapped object, will by default produce bias-corrected accelerated confidence intervals, bootstrap confidence intervals. Okay, and this is quite uniform. So for example, we have a delta method function which calculates estimates, standard errors, and confidence limits for nonlinear functions of regression coefficients. And we can use a non-standard coefficient covariance matrix in that as well. Okay, turning to the data on police stops in Minneapolis, we have a data set with both individual stop level data and that is on the individuals who were stopped by the police, and neighborhood data where the stops take place. So there are a number of neighborhoods. We know the race for many of the people who were stopped, either white, black, or Native American, their gender, female or male, and black is the proportion of residents in the neighborhood where the stop took place who were black. So using the glimmer function in the LME4 package, we fit a simple mixed model to the data, as you see. And that model includes race crossed with gender and an additive term for the composition, the racial composition of the neighborhood, and a neighborhood random intercept. Okay, so the summary of the model, which I'll pass over quickly, by default includes for a logit model, which this is, exponentiated coefficients, that is, effects on the odds, multiplicative effects on the odds scale. But because the model includes an interaction, it's difficult to understand what the model is saying about the data just from the coefficients. So here, for example, are all of the predictor effects in the model. And here is a partial residual plot for the predictor black, which we've assumed has a linear effect, and that seems to be nearly the case. The magenta line is an unparametric regression smooth. The blue line represents the fit of the model on the Logit scale. And here is a customized effect plot showing the race by the race by gender interactions. So clearly, blacks, both male and female, tend to be searched when stopped with a much higher probability than whites, and Native Americans even more so. The gender differences are less for whites than for blacks and Native Americans. Okay, so I think I've exhausted my time. There's a little bit more here showing the use of influence diagnostics for the model that we fit to the data, where we'll discover that a couple of neighborhoods are having a substantial effect on the results of this model, and that the results change considerably, but not entirely, when those neighborhoods are removed. Okay. So.
We have time for one question. Maybe I have a question, which is, do you provide any support for MTCV, for GAN models in MTCV?
No, just parametric models.
Okay.
Yeah. Now, I'm not sure. This is in the effects package, I assume you're asking. What we require is a linear predictor. Yeah, that's essentially what drives it. If you have a linear predictor and a V-cove method and a model matrix method, then the default method either will work or it can easily be made to work. Yeah. Thank you.